linear dependence or linear independence is actually, I would say, difficult to understand, but easy to calculate. So the trick is always, like when you have a two-dimensional coordinate system, you can have at most two linear independent vectors. Like when you have them like this, they're linear independent. When they're like this, they're still. If you just have two and you say those two, then what are they? Then they're also linear independent. But as soon as they're parallel, then they're linear dependent. And why is that? Because their directional vector is they're sort of related very closely, and you can express one directional vector by a multiple of the other directional vector. So you see that the directional vectors are somehow related, and you don't need any third information, just those two and maybe a multiple of the directional vector of one to express the directional vector of the other one. Sounds a little bit difficult, but this is actually already it. And for the three-dimensional case, I will also demonstrate it later. Of course, then you have to look at three vectors, and you can have three linear independent vectors at most in a three-dimensional coordinate system. Sounds difficult? Actually, I think it is not. Once you got it, then you got it, and the calculation is easy. And just have a look at the example in the following clip. How about linear independence or linear dependence? This is actually a topic which I think is a little bit difficult to understand, but easy to calculate. When I first heard of it in class, I could calculate it very quickly, right from beginning, but understanding it is a little bit more difficult. But I'm going to show you the theory, and then we're going to calculate two examples so that you see it's actually not that difficult. Also to understand is not too difficult. But first I'm going to show you the principle. So first, this is a coordinate system, and linear dependence means, or linear independence, that first, let's say we have two vectors. One I call A, the other one that's B. And in this case we see, okay, maybe both vectors don't have the same length, maybe not exactly, just about, but we can say both have the same direction, and then we can say A is a multiple of B, or B is a multiple of A, and then we can say when there's a connection like this between two vectors, we can say they're dependent, or there's linear dependence between both vectors. And it's important to know that there are two rules, or let's say it's one rule, and it says in a two-dimension coordinate system we can have maximum two linear independent vectors. In a three-dimensional coordinate system we can have maximum three linear independent vectors, and so on. And this is important because we'll see it later in the calculation. Maybe I'll show you the principle with the example, but you see it in this coordinate system, in the two-dimensional coordinate system. There are two axes, one x-axis, one y-axis, and we can describe everything that happens with those two axes, which are actually also, you can also say some sort of vectors. And same thing in a three-dimensional coordinate system. There we have, okay, maybe this is always a little bit difficult to imagine, but 3 dimensions, then we can describe everything that happens in the three-dimensional coordinate system with those three vectors or dimensions. And okay, maybe another example how you can imagine linear independence and linear dependence. Okay, let's say we have two coordinate axes, y-axis, x-axis, and we have one vector in our coordinate system. This vector I call A. And then we can easily see that given our two coordinate axes, and by the way, those two axes are linear independent, as we can see, because one has something that the other one doesn't have. if we have 2 dimensions, we see that this is 1 dimension and it has none of the other dimension, right? This is 1 dimension and it has nothing what the other dimension has. It's 90 degrees, and it doesn't have to be 90 degrees, but there we see, okay, it's totally like this axis does totally not have the thing that this axis has. Maybe we can say it with an example. If we have 2 dimensions, we could say x and y. Then we see that the x-axis has maybe these elements and the y-axis has maybe these elements. Then you see easily one has just one component and the other one also has just one component, but in the other element, right? So we can see that this vector A consists of a certain portion of x. Maybe let's say, I don't know, or let's call it maybe B. And it consists of a certain portion of y. Let's say that's maybe C. It means that we can easily construct A when we add B and C. B is a proportion of x, so let's maybe say 1/3 or whatever, or 3 times the x vector, and C is a certain proportion of the y-axis, maybe also 1/3 or 5 or whatever, just a number times the y-axis, and then we can compose A of those 2 vectors, right? And when we can say we can compose one vector of 2 others, then all 3 vectors together are related through linear dependence. Otherwise, if I just look at y and x, both vectors are related through linear independence. Why is that? Because I cannot construct y through x and the other way around. I cannot construct x through some addition or multiplication of y. But if I take all 3 vectors, I can say, okay, there's some linear dependence. Why? Because I can construct A by adding a certain proportion of x to a certain proportion of y, and then I end up with A. And that's actually the principle. And maybe we can have some more examples so that you can understand it. So you may see now that it's a little bit difficult to understand, but actually once you understood it, it's also quite easy. So let's say we have again our 2-dimensional coordinate system with y and x. Then we can construct this vector by a certain proportion of x added to a certain proportion of y, right? So we go certain proportion of x, maybe in this case 1, 2, 3, 4, maybe 1/3 plus 1 times y or so. Then we would end up with, let's say, A, with this vector. And we can also say that we can construct all these vectors. So wherever direction they show, or also this direction, we can construct it. Then we take minus maybe 1/3 of x plus 3/4 of y, and then we end up with the vector again. So we can construct all the vectors just by a combination of those 2 linear independent vectors. And another thing, we could also say, okay, we have our y vector again, and this time we have this vector. So are those 2 vectors linear dependent or independent? And we can easily say, okay, they are linear independent. Why is that? Because I cannot construct this vector by multiplying or adding or whatever, constructing it through the other vector, right? What I could do now, I could say, okay, I could say minus 1/2 y. Then I would end up with this vector. So I come very close to it actually, but I cannot get this direction with the y vector. And that's why y and x are still linear independent. But on the other hand, if I have a vector like this, and I call it A, then I can construct it by taking y and x, by taking a certain proportion of x, because x has a big proportion in this direction, in the right direction, and a little bit of in the minus y direction, and the other vector y has a big just goes in this direction, right? Goes in the up direction. So I could combine both vectors and construct A. So I could say y, a, and x are linear dependent, but y and x are linear independent. Also y and a would be linear independent. A and x would also be linear independent. Why is that? Because I can always have maximum 2 linear independent vectors in a 2-dimensional coordinate system. So if I have 3 vectors, it's always possible to say linear dependent in some sort. I mean, it could be that both vectors are parallel. Okay, then no, they're also linear dependent again. And if they have different directions, linear independent, if I just have 2. But if I add a third one, then I can say, okay, linear dependent. All 3 are linear dependent. If I take 2 in this type, in this coordinate system, I would say, again, linear independent. So I hope I'm not confusing you too much with the definition, but I also hope that you might have understood it or developed or are about to develop an understanding of what means linear dependence, linear independence. So let's maybe have a look at an example. So we have 3 vectors given A, which is 3, 9, 2. The next vector is B, which is 12, 36, and 8. Next one is C. C is 4, 10, and 2. And now we want to know, are those 3 vectors linear dependent or linear independent? And first step you want to do is have a look. Just have a look and get an understanding of the vectors and what might be the solution. This already helps a lot. So we have a look. We just look at 2 vectors and we see, okay, there we have 3, there we have 12. The connection might be 3 times 4 is 12. I have 9, I have 36, 9 times 4, 36. I have 2 and 8, 2 times 4 is 8. So I can say 3 times 4 is 12, 9 times 4 is 36, 2 times 4 is 8. So I can say both vectors are actually parallel because B is the same vector, just multiplied with 4. And this means they're parallel. B is just 4 times the length of A, but the direction is the same. So A and B are parallel. When they're parallel, they're linear dependent. Now let's continue. B and C. So we have 12 and 4. So I divide 12 by 3 and end up with 4. 36 divided by 3. No, does not fit. 8 divided by 3 also. This does not fit. So I can easily say B and C are not parallel. B and C are linear independent. And also I can say A and C are linear independent. Why is that? Because B and A, they have the same direction, and C is different to B, then it has also to be different to A. So all 3 vectors are linear independent. If I look at 2, which is A and B, I can say linear dependent. And if I look at B and C, linear independent. If I look at A and C, also linear independent. Right? Okay. Just by looking at it, I can already solve this type of exercise. So it's actually in principle not too difficult, but of course the understanding is necessary, and also to take it easy, just have a look, try to solve it, and not make it too complicated as it actually is. But then we need, in this case, a mathematical proof. Are those vectors linear dependent or linear independent? So what we want to do is calculate. Actually, the thing I already did in my head would be sufficient if you can really argue with some numbers like I did here and say, okay, A is a multiple of, or B is a multiple of A, and this might actually already be enough, but this actually is a very strong argumentation I'm going to show you. And this works the following. So we say we take all three vectors and try to create the zero vector, or create 0, and then we can show if there is no other solution, then all of the factors are 0, which is called the trivial solution. Then the vectors are linear. What I'm going to say, I say it in a second again. Wait, c times t is 0. So now there is a solution which is called the trivial solution. It is when r, s, and t equals 0. When there's another solution, then we can say the vectors are linear dependent. If there's just this one solution, then we say the vectors are linear independent. And that's the principle you can apply to solve it. You just have to put in your vectors, calculate it, and then you can say if you get this solution, you can say the vectors are linear independent. And if you get a different solution, then the vectors are linear dependent. This is also important to keep in mind, and then we can start to calculate, actually to get to the solution of our example. Now, okay, 3 vectors, and it's actually also not too difficult. You just have to pay attention not to make any mistakes in the calculation now. So these are our vectors. I'm just constructing the equation system. First I write down the vectors. 4, 10, 2 times, what did we say, t. And now the equations, 3r plus 12s plus 4t equals 0. Second, 9r plus 36s plus 10t equals 0. Third equation, 2r plus 8s plus 2t equals 0. Now we can transform this into a matrix. That I actually like matrices a lot because it's quite structured to solve, and you don't have to carry all along those r's plus s and so on, and it makes it a little bit easier, and I would say also quick to solve it. And you have a very good overview over the numbers. And then we can also solve it with the Gaussian algorithm, which is actually also quite simple. It sounds difficult, but it's not difficult. Okay, so this is our matrix. So what I did is just copy the coefficients. That's how it works. You just copy the coefficients and the solution, and there we need separation, and then this is r, this is s, and this is t. You have to keep in mind, and then the goal is always we want to get something like this, maybe 5. This is not always 5, it's just an example, and 7, and then you see easily, okay, we say r, 1r is 5, 1s is 6, 1t is 7. That's what we want to achieve with this matrix, and that's actually everything. That's what the Gaussian algorithm says. What's the principle, how to solve it. So we start with 1. We say 1a, because I already saw, okay, there's 3, there's a 9, 3 and 9 fits together. 3 times 3 is 9, so we can create a 0 here. And by the way, it doesn't have to be this nice step view. It can also be that maybe first row and third row are switched, or whatever, first and second row are switched. It doesn't really matter, because you can, of course, it's like here, you have to keep in mind that this matrix bases on those 3 equations. It's a 3 by 4 matrix. so means 3 equations and 4 or 3 rows, 4 columns. And it means that we have 3 equations, and of course when we calculate we can always write the first equation maybe at the end and call it differently. We call it, we don't call it 1 but 4, then we have 2, 3, 4 and no 1. We can also always do this, but it's always easy just to start and to look for like those how to say, numbers that fit together, like 3 and 9 fit together very well, as also 12 and 36. I could also say 12 times 3 is 36. Okay, 4 and 10 maybe more difficult, but 4 and 2 I can say 2 times 3 equals 1, and then I can create zeros. But I'm going to show you now how it works. So I say I take 1 minus 1/3 times 2. Okay, then I have 1a, and I just write it down. 3 minus 1/3 times 2 equals 0 in this case. Okay, 12 times minus 1/3 times 2, also 0. Now it may become more difficult, so I take the calculator just to be sure. I have 4 minus 1/3 times 10, and I end up with 2/3. And here that's 0, 0 minus 1/3 times 0, of course. This is a 0. Then what else can we do? We can say 2a is 2 minus 5, 3. And then we can create a 0 here, right? So we say 2 minus 5, 3, just 2a. So we have 2, 9 minus 5 times 2, okay, minus 1. Maybe we can also calculate it in our head. 36, now it gets more difficult. Minus, when I have a calculator, usually I always calculate it with a calculator, just to be sure. Minus 4, okay, also. And then we said, okay, 10, so we create the 0 here, and we end up with the 0 at the end. Then what we can also always do is just, okay, maybe I'll do that later. Now what else can we do? 3a, I say. And we take 3 and say, okay, we want to eliminate maybe the 9. So we say, we take 3 minus 2a. And okay, maybe we can do actually, what we can always do is also we can multiply one entire row with a number, or we can divide it by a number, or we can also maybe multiply with minus 1, just to make it easier, so that the signs are maybe not minus but plus, and that it's easier to calculate. So in this case, it's what I want to do. I multiply 2a with minus 1, so it just ends up with positive numbers, and I can easier calculate. So then I can say I take 3 minus 2a, and I end up with 0. Then 8 minus 2a, also 0. 2 minus 2a, also I end up with 2, and of course here it's 0 again. Then what can we say? Okay, we can say t, 1t is 0, so t is 0. We can say the second component, s, we don't know actually, because because the first row and the last row tell us the same information, right? T is 0, t is 0. If I divide or multiply by 3 divide by 2, then I end up with 1t equals 0. And here the same, divide by 2, both sides, then I end up with t equals 0. So t is always 0, that's clear. But second component, I don't really know. But there's a relationship between the second and first component, which is the following. So I have to insert parameters. So I first say second component, which is s, is a w. And then I can say first component, which is r, is minus 4w. And w is a number which is element r. So I have a very general solution. I know the third component for sure, but the first two components, r and s, I'm not 100% sure, because I have to introduce a parameter. But I don't know the exact solution, but I know the relationship between the first and the second component. So this is an indicator. Then this is a mathematical proof that we have that actually our three vectors with which we started, A, B, C, are linear dependent. And we could also now argue that A, B, and C are linear dependent. A and B are linear dependent, but A and C are linear independent. And B and C are also linear independent. That's what we said in the beginning, what we all already found out just by having a look at the exercise. But when the question is, are A, B, and C linear independent, then we can say no, they're not linear independent, because the calculation showed clearly all three vectors are linear dependent. So that's our first example, and now I want to calculate another example, because we just had linear dependence now, and to make it complete, I want to show you how it works with linear independence. So we have three vectors. First vector is A, minus 6, and 8. B is 4, minus 7, minus 5. C is 278, 74, 66, three vectors. Now we apply the same procedure as before. We say we have a look. So how does it look like? Minus 6 and 4. You can also look for numbers that are easy to calculate in the head. And here actually it's easy. You can say, okay, I have two components which are the same. Then I look at this vector and say, okay, both components are not the same. So whatever I multiply the vector A with, I would never end up with these numbers. Why is that? Because both elements are the same, and here they're not the same. So I take it times 3, and I would end up, or take it maybe with some multiple, and I would never end up with this. And I could also apply this principle to the vector C. So I can definitely say we have linear independence, that A and B are linear independent, and A and C are linear independent. And what else? I can have a look at B and C, and then I see, okay, this may be a little bit difficult to calculate in your head. You can also say, okay, maybe I leave this for now, because I already know the complete solution. All three vectors are linear independent. If you want to prove it, or if you want to think more, then you can always say, okay, 74 divided by 7, then you know 10.57. And if I divide by 5, I end up with 13.2, so I also see that B and C are actually also linear independent, because there's no multiple that I can use, or I cannot multiply B by any number and end up with C. It's not possible. Also A and C, not possible. A and B, also not possible. So all three vectors, and always two of them are always linear independent. That's what we can say just by having a look at it. So we already know the answer, and now we want to calculate a little bit to really have a good and nice proof. Same principle again. A times R plus B times S plus C times T equals 0. then we can write down our equations. Minus 6r plus 4s plus 278t equals 0. Second one, minus 6r minus 7s plus 74t equals 0. So what I do is just take the first components for the first row, second components for the second row, third components for third row. So third equation, 8r minus 5s plus 66t equals 0. Then I transform it into a matrix again. You see, okay, here I need to also take the minus sign. Is also important to take it with you in the matrix. We have minus 6 for 278, 0, minus 6, minus 7, 74, 0, 8, minus 5, and 66, 0. Then we have our matrix, and then we can start to solve it. So we start with 1a. What can we do? Of course, we see minus 6, that's perfect. We can just say 1 minus 2, and we end up with 1a. Then we have a 0. 4 minus 7. No, we have again 4 minus 7. Yes, and we end up with 11 because then it's positive. 278 minus 74 is 204. Okay, we can also do it in our head. Then 0. First row. Now the second row, what can we do? And also one thing you have to pay attention to when you use the Gaussian algorithm, you should not do the same operation several times, because then you might end up with going around in a circle that you may end up with one of these 3 rows again during your calculation. So you always have to pay attention and to try to mix or to put together rows that you haven't put together so far, right? So that you make use of all the information given by those 3 rows. So we say, also to calculate with the third row, we say 2a is 8 times 2 plus, because the sign is different, plus 6 times 3. Then we have 2a, and we end up with 0. That's not too nice here in the front, but we can do it because we have our calculator. So not a big problem actually. So we can just calculate it. Minus 7 plus 6 times minus 5 minus 34 and minus, no wait, I think I made a mistake. Minus 7 times 8 plus 6 times 2, 3, yes, minus 5. Minus 86, my mistake. 86. Then we have 8 times 74 plus 6 times 66, where we end up with 988. Okay, these numbers are not too nice, but we can calculate it anyway. And we end up with 3, 8 minus 5, 66, 0, and then we see, okay, there is one problem, because we see 0, 0, 0, 0, that's okay, but in between we see that it doesn't really work out. We have here a variable, and here, and also the multiple is not the same, like the relationship between those two variables, between s and t in this case, like this is our s column, this is our t column, this is our r column, By the way, you should always write down R as a T element R, and we see that there's a problem because the relationship between those two variables, between S and T, seems to be a different. So both informations from first and second row are contradictions. So it does not really work. And if there's a contradiction, it always means that there is just one solution, which is, as you might remember, as I told earlier, if there's only one solution, it's usually the trivial solution, because of course when I want to solve this, I can always say R and S and T are 0. If all those factors are 0, then of course my equation is fulfilled. It's always true. But the thing is, when you calculate and you find a more general solution, and for example, as we had it earlier with linear dependence, then you can follow that there's linear dependence. But in this case, we end up with a contradiction. So the only solution possible will be that all our three factors R, S, T are 0. And when you calculate this, maybe you continue to calculate, then you will see, or you can also calculate it with a calculator, which can do this. But in any case, you will end up with this sort of matrix, if you calculate it correctly. And this tells us like 1 R is 0, 1 S is 0, and 1 T is 0. So we see that the only solution is 0 for all three factors, and when we have this solution, then we can say, okay, we have linear independence. So this is how it works. We calculated two examples, quite a lot of numbers to calculate and a little bit difficult. Also the principle is maybe a little bit difficult to understand, but you saw it's possible to do, and the principle is always the same you have to apply, and all you should do is practice, and the more you practice, the easier it gets. Just keep in mind maybe this is important, the definition of linear dependence. If this only has the trivial solution, as I said earlier, which is R, S, and T are 0, then you have linear independence. If there's another solution, then you have linear dependence. And you can also apply this, okay, maybe in the two-dimensional area it's much easier. You can also say, you can shorten it a little bit to 2 vectors, or also extend it if you have more vectors, and you can check it. And if you have, of course, a calculator which can do the calculations, it's much more easier, like to calculate with matrices, but this calculator cannot do it. We need a special one. And another thing is, in a two-dimensional coordinate system, you can have maximum 2 linear independent vectors. In a 3-dimensional coordinate system, you can have maximum 3 linear independent vectors. And you might remember also the picture I drew earlier with the coordinate system, and you can always maybe memorize it like this with the coordinate axis. You have 2 coordinate axes in the 2-dimensional area, and 3 coordinate axes when we're when we have 3 dimensions. And those 3 axes we need to construct everything that happens in between. And best thing is you practice, and with practice you get some speed in it, and then you will also be able to solve this type of exercises quite easily in exams without mistakes. So this is how it works. Thanks for watching. Practice makes perfect. Further exercises with solutions you can find on my website, which is www.worksheets.com.